right. I'm switching to English. And first of all, it's really a pleasure to be here talking to all of you that then will also be talking to the new generations of girls and women in science in Catalonia. And I wanted to give you a taste of what I do, how I got there and why. So the title contains particle collider, so that will be the center of my presentation. I will explain what the standard model is and why I want to go beyond it. So first of all, a bit of the trajectory, because a scientist nowadays travels all around the world, and it's, I think, part of the appeal as well of doing fundamental research. I was born in Argentina, and I then moved with my family to Spain. And in Canary Islands, in Tenerife, I studied physics in the University of La Laguna, where at the end I got the Premio Nacional Fin de Carrera. This was a fantastic journey because, if you know there, the skies are amazing to do astrophysics. So that was my first direction. Then it changed into theoretical physics. But finally, news from the start of the Large Hadron Collider at CERN reached to me, and I started doing some research, and then I was caught until now. And that meant I wanted definitely after my studies to do a PhD in particle physics as an experimental physicist at CERN, working with one of the experiments of the Large Hadron Collider. So I started my PhD in Göttingen in Germany. I was also supported by a female grant that was supporting women in science, the Dorothea Schlözer program. And this allowed me to be, from 2010, a member of this enormous collaboration, which is the ATLAS collaboration of one of the main detectors at the Large Hadron Collider, that has, as you can see, over 5,500 members. So it's really gigantic, almost a mini society. And after that, I was still caught into this topic, and not only that, I really wanted to be in the hub where everything happens, which is CERN. It's located, the accelerator complex between France and Switzerland, and I managed to become a postdoc researcher with the McGill University in Canada, but based at CERN, which allowed me to be close to my collaborators and also to take part actively there in the control room, as I will show you next, of the ATLAS experiment. And I was so caught that then I also got the CERN Research Fellowship for 2 years, and afterwards I was a CERN research physicist. Until I came back to Spain with the Ramón y Cajal grant, and I was extremely happy to join a fantastic team in the Institut de Física de Altas Energías here in Barcelona. I'm there a tenure track since 2024. And a very nice surprise came right afterwards, which was winning the ATRAE 2024 grant, which also allowed me to be a principal investigator of my own project. So now I have students, and soon I will have also a postdoc. So to explain what motivated this journey of several years, it's a passion. And the passion of becoming a high-energy particle physicist. And for those that are not familiar with it, I want to give you a taste of why this is so exciting. So first, focusing on the particle physics part of it. So here I'm trying to search for the absolutely most elementary, fundamental building blocks of the universe. So we know that matter, it's made of molecules, atoms, which are made on its own by a nucleus surrounded by several electrons, in a very simplistic, of course, classic view. And then the nucleus is also made of protons and neutrons. These are also not elementary because each of them, protons and neutrons, are made of quarks, which also have inside gluons. And these gluons and quarks are what we call elementary particles. If we put it all together, our current view of nature can be summarized and condensed in this tiny box where I show the standard model of particle physics. This is our current understanding of the elementary building blocks of nature, which are the fermions here, the quarks at the top, and the fermions and the leptons at the bottom. You see that also there is some type of symmetry between leptons and quarks because they come in these 3 generations. And then we also have, because these at the end of the the story, it's a quantum theory, we also have particles associated with the forces that interact between the particles and sometimes among themselves. So here is where we have the photon, the weak bosons, and the gluon. Here at the center is the Higgs boson, and I'll definitely dedicate at least a slide later on to it, because this happened during our lifetime, and we were so excited of discovering it. And with this, the Standard Model closes. But what is interesting is that nowadays, in the world that surrounds us, we can basically make up matter and interactions with basically the first generation of quarks and leptons, and that's it. So where does all these second, third generations come? It means that nature is really more than just what we see or can perceive in our surroundings. So here is where the high energy comes as highlighted part of what I do. We're here today in this very simplistic vision of the universe in time. So we believe that we have come from this Big Bang explosion. There was an inflation period where the universe accelerated and expanded. And then from that point onwards, the universe started cooling off and still expanding in an accelerated mode. So in a way, right now I only see these particles because I don't have enough energy to create the other much heavier particles. The only way to do that is to basically go in a way back in time, in the sense of getting into these moments where the energy and the temperature were so high for these other heavier particles to exist. But how do I do that on Earth in a controlled way? This is where particle accelerators and detectors come into our scene, because they allow us to access these very heavy particles that only existed 10 to the minus 12 seconds after the Big Bang. And it's really with high energy when we manage to basically unveil the inner structure of the universe. That means to really understand these fundamental laws of the full structure of nature. And this pushed many scientists to build this, what I find such a masterpiece of the CERN Accelerator Complex and Collider. So we talk a lot about the LHC, but as you see, the LHC is only this last ring, the big one here. But before that, there are several stages of acceleration. We start from a bottle of hydrogen. We extract the protons from there. And then from this LINAC, we start progressively accelerating from LINAC to booster to proton synchrotron to the superproton synchrotron. And from there, we have two beams of protons injected into the Large Hadron Collider at this energy, 450 gigaelectron volts per beam. They continue accelerating until we reach these incredible collision energies that have, as you see, increased throughout the different runs of data taking. And once we reach the collision energy desired, we collide them. And we'll talk a bit more about that next. But since we're here in Barcelona, I cannot go ahead and without talking about the ALBA synchrotron. And I would like you to have also some perspective of an idea of the dimensions, make a brief comparison with the ALBA synchrotron. So actually, the way of accelerating in ALBA takes a lot of inspiration in the CERN, both the LHC, but also LEP, which was the previous accelerator and collider. But you can see that the magnitudes we're talking about are quite different, and also their purposes. So here we are talking at the LHC, it's a 27 kilometers ring of circumference. In ALBA, we have 268 meters ring. In the case of ALBA, we are accelerating electrons, also, fundamental particles, at an energy of 3 GeV. At the LHC, we accelerate protons, mostly. And finally, we have a synchrotron light coming out from basically the simple acceleration of electrons in a circular trajectory, whereas the endpoint here at the LHC is to actually collide the protons. It's very nice to see also in this timeline that you can find in the ALBA webpage, how also the beginning, the birth, and also the first activity from both the LHC and ALBA actually aligned quite nicely, being 2009 and 2012 the starting point of both of them. There is one more very important verb here, that after we collide, if we don't put anything there, I have no idea what happened. So the key part and where I'm working is the detection part. So these 4 interaction points that we have here, the Atlas, CMS, LHCb, and ALICE, these are the points where the protons collide, and I need to have something around these interaction points so that I can actually detect what happened. And in the case of Atlas, which clearly I'm biased to present to you here, these are one of the, what we call multi-purpose particle detectors. These are giant, also constructions that have this onion-like structure, so different layers surrounding the interaction point, and each of these layers are made of different materials so that I can detect and register different type of information of the particles created. So that if I put all together all this information at the end, I have enough hints as a detective to know what type of particle this must have been. So here is where actually IFAE was such an attractive place to come, because IFAE was in the birth of the Atlas experiments and joined it in 1992. It had also a central role in the design of one of these internal layers, which is the tile hadronic calorimeter. It's a part that will force the particle that was produced, if it's hadronic, of a hadronic nature, to basically deposit all the energy in this layer so that I can measure it. So here you can see, for example, an image of this, the construction of the tile calorimeter in IFAE before it was sent to CERN. There's been also a lot of development and operation of the part that takes care of acquiring the data from the detector, and also choosing the selection system, because we cannot keep every single collision. We need to make certain decisions based on what is interesting, and this is a part actually I'm working on. And as I will show also later, we're already now thinking about the future, because this needs a lot of planning. So also IFAE is involved there. So what's the point of colliding? And I was talking about registering particles. What does this exactly mean? And here is the one mini formula that I will present, but that one for sure you have seen before, and maybe it's related with my t-shirt. We basically have these 2 incoming protons going head-to-head in this collision. Each of them have an insane amount of kinetic energy. So to have an idea, the proton kinetic energy is around 6,900 times the proton mass. So even though the proton is fairly light, the energy is incredible. So by E equal mc squared means that I'm transforming the energy, the kinetic energy, into masses of new particles that can afford to be heavy, because I have a lot of energy to create it. So we have this collision, and then these new particles that you see, for example, here in violet, could be one of these particles of the 2nd, 3rd generation that do not exist in our everyday life. And they're so heavy that even through, as they are crossing the detector, they will decay into lighter particles. So I will never see, for example, a top quark, which is the heaviest elementary particle, or even a Higgs boson. What I will see are these lighter particles in which the Higgs boson, the top quark, decays to. So these long-lived end particles. And one more thing is that also we have quite some work to do, because it's not just 2 particles that are very clean and create new particles. Protons, if you remember, these are composite particles. So when I'm colliding it, I'm actually colliding all the internal constituents, quarks, gluons. So aside from the main collision, which is the one I want to focus on, there will be a lot of garbage flying around. So I need to develop, and there is, for example, where machine learning comes into use so much, to be able to distinguish the interesting collision from all the other noise. So the LHC, and also the high luminosity LHC, which is what will happen from 2030 until 2041, was planned a long time ago, as you see here. I was quite lucky to start my PhD. I was quite lucky here to start my PhD at the very beginning when this was conceived, and lucky also to be a witness of many years of operation, but especially to the biggest success of the LHC to date, which is the discovery of the Higgs boson. We're also right now here, so many years have passed, and I will talk a bit what happened also afterwards. But first, let's dedicate a slide to the discovery of the Higgs boson, because what is impressive here is that both ATLAS and CMS discovered the presence of this Higgs boson, with which we had evidence, we could confirm the mechanism by which all these fundamental particles acquire mass, which is the Higgs mechanism. So this was incredible because the theory that had predicted the Higgs boson appeared in 1964. So we required 50 years to be able to get a machine that would confirm it. I mean, I can imagine, and it was clear how emotive this moment was for the theorists, which later on received the Nobel Prize the year afterwards. So this is a very nice, let's see again. We can do it. This was a very nice, what we call histogram, where you see the mass of two photons, which is in which the Higgs boson decayed. So if I calculate the mass of the two photons, I can calculate the mass of the Higgs. And you see here in the GIF, basically, as we add more and more data of the collisions, how clearly these points, which are the data collision, follow the background, which is this noise that I don't care about, but then there is a bump. And this bump does not follow the background. And this bump happened to be at around 125 gigaelectron volts, which is where the Higgs boson was predicted to be of the many possibilities when scanning this range. So by now, but after 2012, we've had so much more data, so now it's absolutely clear that there is a new particle. But at the time, you can imagine the emotion that it was to have found basically the last piece of the puzzle to complete the standard model of particle physics. But why did I have beyond in the title? The standard model of particle physics is not the end of it, otherwise we would have probably finished analyzing our data. We know there has to be an extension of it because there are a lot of observation and also conceptual inconsistencies that the standard model just cannot explain. And I give you some of them here. We have no gravity, first of all. We know gravity exists, and this is one of the first forces that humans were aware of. But there is no verified theory of quantum gravity. We have no explanation why neutrinos have a negligible, non-zero, but negligible mass. There is no explanation why the Higgs mass is actually not that large. So are we fine-tuning a lot of parameters, or maybe there is something else there? No dark matter. You listen about dark matter. Astrophysically, we have observations of its existence, but there is no candidate in the standard model to explain such a type of matter. And similarly, no dark energy explanation within the standard model. We also are made of matter. You know, there is also antimatter. So we would have expected the standard model to predict this asymmetry that would explain the dominance of matter today, but it's not enough. So is there maybe something else that compensates this? Why do we have the three generations of fermions? And why do we have such a hierarchical masses of the fundamental particles? That means that the coupling of these particles with the Higgs boson changes a lot. So a lot of open questions for this being the end of the story. So at this stage in time, I'm very much involved in direct searches for these extensions of the standard model. And theorists are very creative, so we have a ton of these models around that could explain what is missing to the standard model. You see here that unfortunately, there was a gap in the timeline between the discovery of the Higgs boson and right now, because we haven't discovered anything yet. So we have instead set a lot of limits of excluding the possibility of all these different type of hypothetical particles of existing. And we are already, as you see in some cases, excluding 1 teraelectron volt particles. This is actually much more exclusion than the theorists were hoping for. But we need to be creative. We have to continue. And one of them is the leptoquarks. And here, let's go back to the poster, where I actually had the pleasure to choose my favorite model to be represented here. So here you see the leptoquark. This is a hypothetical beyond the standard model particle. It's a very weird one because it has a coupling. It interacts with a quark and a lepton. Really, no other particle does this. And the reason why this one is so interesting, it's because despite not having done an observation of a new particle since the Higgs boson, there are what we call anomalies happening. So they keep us, let's say, with hope and motivated to try to understand if these anomalies, these tensions of some observations between the standard model and data, are they maybe due to some new physics? And here I'm not going to go into detail, but LHCb, which is a third of these 4 detectors at the LHC, they're very focused on particles that contain big quarks or C quarks, the beauty and the charm quarks. And they've observed this tension, which is basically the distance between the red circle here and the crosses that show basically the standard model prediction. This tension has been there for 10 years now. So it has preserved by adding more data, it's still there. So I'm particularly excited about it, and I want to understand whether the standard model process can be maybe complemented by this other beyond the standard model process with the laptop work. This is how it would look like. So this is an actual real data event that looks very much like this type of decay chain of lepton quarks into the top and the lepton, which then the top decays because it's heavier. So then we basically have all this chain of particles that are detected. They have been detected. But one thing to keep in mind is that in particle physics, we can never say things 100% certain, not because we are not so good, but because this is quantum physics. This is all probabilities, and we can only talk in statistics terms, not in absolute terms. So this looks like a data event candidate for a laptop work. So one more thing, because while doing the illustration, actually there was a back and forth with the illustrator and the team on what an experimental particle physics does. And this changes also a lot. We are many, in these 5,500. There are some that have more of an expertise in computing scientists, or others are more in the engineer side. Others are more mathematical in terms of modeling these theoretical models. In my case, my day goes a bit around like this. I do all this analysis of particle collision data, which I love. So there is a lot of coding, physics analysis, and also the trigger software that selects the events. But I also take part in the operations of the Atlas detector. So we need to build it. We need to see that it works. But then somebody needs to be there 24/7 to make sure that it's working as it should. So it's really, at some level, the job of the hospital shifts, that somebody needs to be there all the time making sure that it works. Then, in order for this to not be stagnated and a bit repetitive, that we don't turn the crank every time and just repeat things with more data, we need to brainstorm. So there are a lot of opportunities that we need to create to discuss with other physicists that can be theorists as well. We present also our results at international conferences. We also, very importantly, for this huge collaboration, we need to have different physics groups that need to be led. So I got, for example, the chance of leading the exotics physics group convener of around 500 physicists. So this also develops quite a lot of other skills. And last but not least, one should always remember to go underneath 100 meters underground and visit from time to time the detector that provides all this wonderful data. And my last slide, I need to talk about the future, because as I said, we still have ahead until 2041. So this is already planned and set, and it will happen. But already now we need to think what happens beyond 2041. So this year is very important because we're finishing the data taking of what we call Run 3. So there will be then a period of a few years of upgrading for high-low LHC. But as I said already, the European strategy for particle physics is thinking what to do beyond. There's been a lot of back and forth with the different member states, for example, Spain, on what should we do next. And now it has been recommended that the so-called Future Circular Collider is the preferred option as the new flagship collider at CERN, and that, again, will be from the European side, our flagship. It has also been included among the 11 proposed so-called moonshot projects by the European Commission. And so that you get a sense, this is really impressive. The LHC that we thought it was so big is this tiny circle here of 27 kilometers only. And the FCC would be 91 kilometers circumference. So this is really impressive. It would allow us to collide electrons, to collide hadrons at around 85 tera-electron volts. This is really, for me, super exciting, and we need to make sure that also the new generations find this exciting, because the only way to go through all those years of research is to keep the passion alive. So I really hope that this more than a dream will be the future. So I can only tell all of you, because I'm sure you know this, we just need to continue searching, because I'm sure we'll be discovering soon. Thanks.